topics are going to be, let me take this off. What are they? Where do they come from? Why are they regulated? I'm glad they are, by the way. Different chemicals that we can use, of course, equipment. And if you are redesigning a chemical program, or if you have you're putting in a new system, we'll talk a little bit about things to talk about and look at. So what are they? There are these metals or metalloids that are toxic to microorganisms. And these are, anybody know what those are? From your old biology days?
This looks like a water bear.
Yeah, something like that, yeah. I think they're copepods. But a lot of times when they do those toxicity tests, they use Daphne, magna, maybe another small water flea like that. So we look at the periodic table, and here's some of the cast of characters we're talking about. Actually, that doesn't look quite right. Those red circles are supposed to be up a little higher. So we're talking about chrome. Not as much chrome as there used to be out there, but people still use it in especially military applications. There's a lot of chrome still being used. Nickel, really popular. Copper, zinc, all three of those are pretty prevalent out there. Silver, cadmium, palladium, gold, lead, what am I missing? Selenium. Primarily it's the nickels and zincs, coppers of the world. Again, sometimes chrome, we'll talk a little more about detail into chrome in a bit. Did I miss anything? Anybody treating anything exotic out there like molybdenum or selenium? Which one are you guys getting hit with? Molybdenum? That's not an easy one. Not an easy one to get rid of. We'll talk about that in a minute. And yeah, this is supposed to be moved up. I'm not sure what happened. But selenium and molybdenum are the ones that are kind of the new heavy metals that the environmental agencies are starting to kind of crack down on a little bit. You know, the power industry, you know, copper piping. I've got some customers that have higher copper coming in their plant than they do going out because they have copper piping. Sometimes they've got galvanized piping. Sometimes their nickel's higher or zinc is higher than coming in than it is going out, believe it or not. You know, this is a shop where they're doing putting paint on parts. Obviously, they're digging for some kind of heavy metal there. Any of the plating or the printed circuit board shops, a lot of copper in there. And this is just a plating bath. So all kinds of industries, I'm sure we're missing some. So what happens? So these things bioaccumulate. You probably have heard that term before. So they go into the sediments after they're, you know, going into the watersheds, and these zooplankton, you know, Daphne magnas, the water fleas, what does he call it, water bear? All these different microorganisms or zooplankton are eaten by fish and then by birds. And sometimes we eat the fish and sometimes we eat the birds. And that's not good for us, especially if you're a pregnant lady. So obviously some of these metals are worse than others. You know, cadmiums and mercuries and leads are really, really bad. And you don't see those very often, and chrome. But chrome's really easy to treat. So we got to get them out of the water, right? We got to pull them out by precipitating them. Otherwise, they stay soluble and they don't come out. So we have a solution that's full of zinc, let's say, and we add our precipitant and we precipitate out a precipitate. So we're pulling that metal out of solution. A couple ways of doing that we're going to discuss here in a few minutes. All right, hydroxide precipitation. Most people, this is what they do. Not always the best in terms of overall results, but if they're using it, they probably don't have real high heavy metals to begin with. So yeah, here we go. Our old friends, the pH analyzer and the pH probe. This is why pH is so important. You've got to have you got to have equipment that is calibrated and works, or you're going to have, and in particular, when you're treating heavy metals. So we have a situation where we have lead and we have chrome. Two very different pHs. Can be a problem for some people if they have metals that precipitate out at different pHs. So if you look down on the bottom there, so where is chrome going to come on? About 7.5, whereas lead maybe more in that 10 range. So you can see where there might be challenges for some customers. So what do? You treat for the one that is giving you the most problems, and you hope for the best in some of these other things. So when we talk about hydroxide precipitation, we're talking about a very, very closed lab environment where they're coming up with these curves. So in the real world, let's pick chrome. In the lab environment, it says 7.5 is the best pH. Well, at your facility, with a mix of chemicals and metals and everything else in the water, it might not be 7.5. It might be 8 or 8.5. So one of the things that's important that we do is we look at, in the real world, where's the optimized treatment. And some of these things are really great to use to get you in the ballpark, but to really help you out, you need to do it on site. So amphoteric, does anybody know what amphoteric means? Maybe you did it one time and you just forgot, right? So when we look at chrome as an example, you see that it comes down, and the best or the lowest concentration of chrome is 0.1. And then as you watch as the pH goes up, it goes back into solution. That's what amphoteric metals are. They kind of have this kind of U-shaped form in terms of their solubility. And some of those are pretty tough. Chrome is actually one of the easier ones to treat. So, and this is kind of a joke, if you're really interested in what the solubility constant is, anybody want to read that? I'm kidding, probably not. It's one of these things that's mind-numbing. If you really want to know what a solubility constant is, you can check this out. So, okay, what are the advantages of hydroxide precipitation? Relatively inexpensive, and if you have a ton of metal, it's really easy to treat in most cases. What are the disadvantages? If that pH changes, if you have that sludge stored in a sludge thickener, that pH may change, and those metals may resolubilize. So you may have a higher reading when you're running, as an example, running this waste through your filter press. So what's coming out the filtrate may have higher levels of these metals than you would like. And it does create a lot of sludge. But again, if it's not a F006 listed hazardous sludge, that might be okay, because you're just putting it into a dumpster and it's not that expensive anyway. Yeah, like I said earlier, it's, some of those metals might be way off in terms of where their solubility or insolubility is. One might be at a pH of 6 and one might be at a pH 11, and that makes things difficult. And again, you got to have a pH probe and an analyzer that are calibrated and working, or you're going to have a big mess on your hands. And I can't tell you how many times I work with people and they have issues, and the first thing I ask them is what? You guys know what I always talk about. Did you calibrate your pH probe, right? When's the last time you calibrated your pH probe? And if it's off by 0.2, we're okay. But if it's off by 2 points, you can see what can happen. Not good. So the second type of metal precipitation is sulfide. Again, uses the solubility constant to precipitate it from the water. So basically what that means is they take the highest concentration of metal that they can get, supersaturated solution, and then they treat it. So that's basically what all that gobbledygook was about. I'll summarize it for you. So all of these metals, and if you take a look at the left-hand side, is that the X or the Y? I forget how that works. I think that's the Y, right? That's the X, okay. So the X side of the graph here, look at how low they can go. We're talking about, on the bottom, 10 to the negative 13th. So what does that tell you about sulfide versus hydroxide? Well, I'll tell you what it means. If you have really, really low metals limits, you may have to use sulfide precipitation because it's the only thing that will allow you to get to some of those really, really low numbers, like a 0.01 or 0.0 anything. You may almost have to go to sulfide unless you're really lucky and your hydroxide precipitation works out real well, or you've got filtration or other things. So, and on the other side, there's actually two different types of sulfide precipitation. You can use an inorganic and as well as an organic form of sulfide. And we'll talk a little bit more about that. But in general, if you really need to get those numbers down, sulfide may be the best option for you. And again, I threw that in there because I know it's mind-numbing, and if anybody really wants to read that, feel free. So there's the inorganic sulfide. So less pH dependent than hydroxide precipitation. So you can not ignore your pH probe, but you can, it's not going to be as critical. Very, very common. You just don't create as much sludge. And those metal sulfide complexes, if you're running the sludge from your sludge thickener through your sludge press, if someone's doing a T-clip, you're going to be okay. Whereas with hydroxide, it might not be exactly what you thought it was, because that metal might be going back into solution. So sulfide is it forms a really insoluble complex, which you can't say with hydroxide. So slightly more expensive than hydroxide. We do have challenges because of the odor that comes off. I know I have customers that have issues with odor that they have to put equipment in to take care of it. It can be a little bit of a handling issue. It kind of turns your fingers black and things like that, which, isn't a huge deal. So then we have this other thing called organic sulfide.